Hey you! Welcome to the second episode of Understanding Schemes. Now, it's been a while since the first episode, so if you need a reminder, link for the first episode is going to be in the description, but let me just shortly recap what we did. So we laid down the foundation for classical algebraic geometry over algebraic closed fields, so fields where k bar is equal to k is usually the shorthand that people use. And we motivated the duality between algebra and geometry using Hilbert's Nullstellensatz. In particular, we saw that there is a duality between points in affine n space and maximal ideals in the polynomial ring. We started thinking about generalizing this perspective by taking the set of maximal ideals of an arbitrary ring and trying to form it into some sort of geometric object, which we'll call MaxSpec, the maximal spectrum of that ring. But before we get into that, we want to see that this theory, this correspondence between algebra and geometry, doesn't only work for affine n space, but actually for every algebraic set. Let V be an algebraic set, which is defined by the ideal I, which is a radical ideal. So in other words, I of V of I is going to be I. So this, as we saw, is the same thing as taking the radical. So this means that I is a radical ideal. Now, we can view the ring of polynomials in n variables as a ring of polynomial functions on Kn, on affine n space, simply by taking a point and, for any polynomial, just evaluating it at that point. We want to get a similar idea for any algebraic set, so some notion of a ring of polynomial functions. So we define the coordinate ring, but this is going to be the set of all functions from V to K, such that f is equal to the restriction of some polynomial map. So, in other words, all maps on V that can be represented by polynomials. Now, at this point, it's worth mentioning that generally polynomial and polynomial functions are different. There can be two polynomials which are different but yield the same polynomial function, but over algebraically closed fields, and in particular over infinite fields, we don't have to worry about that. So for us, polynomial functions and polynomials really are the same thing. I'll also note at this point that polynomials, when we endow affine n space with the Zariski topology, are continuous, but not all continuous functions are polynomials, and same thing, these functions in the coordinate ring are going to be continuous on V when it's endued with the subspace topology, but not necessarily all continuous maps are going to be polynomials. It's worth also noting at this point that this presentation of a polynomial function restricted to V is not unique. So for example, take the set V to be V of the ideal X contained in K2. So we're thinking of the polynomial ring K of xy, we're taking the ideal generated by X. Then this is exactly the y-axis. It's the points at which X is equal to 0. So this is this set. Now consider these two polynomial functions. So f of xy is going to be equal to y squared plus x squared, and g of xy is going to be equal to y squared minus x squared. So these are obviously two different polynomials, but if we restrict them to v, then of course they just become y squared, which is the same polynomial. So we got two different global presentations for the same polynomials on an algebraic subset. Now, it would be useful to get a more algebraic description of the coordinate ring. So consider the restriction map from polynomials to the coordinate ring, given just by taking a polynomial, considering it as a polynomial function, and then restricting it to V. Now, what is the kernel of this map? So what are the functions with that restricted to V vanish? Well, that is exactly the ideal of functions that vanish on V. In other words, the kernel of this restriction is exactly equal to the ideal of V, which is I, but in our previous notation. Now, this means that the coordinate ring can also be written as a quotient of the polynomial ring by the ideal I. So by the ideal of V. Now, because this is a quotient of the polynomial ring, this actually allows us to descend the Nullstellensatz into the coordinate ring as well, giving us the same bijective correspondence between radical ideals and algebraic subsets of V, endowed with the subspace topology, and also gives us a bijective correspondence between maximal ideals here and points in V. So again, we get this algebraic analog to our geometric object, and we recover the geometric object by taking maximal ideals. Now that we have this correspondence also for general algebraic sets, it makes sense to try and define MaxSpec. Now, one perspective that we will cling onto for dear life as we try to bumble through this is that the ring R that we are considering is going to be a coordinate ring on MaxSpec on its set of maximal ideals. And we'll now explain this perspective. So first of all, for a ring R, we define MaxSpec to be the set of maximal ideals, and now we want to topologize this thing so that in the case of the coordinate ring, if we plug in the coordinate ring for R, we'll get something that's homeomorphic to the original algebraic set, thereby recovering the classical case from this new generalized case. So, how do we do this? Very simply, actually. For an ideal I of R, we are going to define V of I to be the set of all maximal ideals M, such that M contains I. So we are going to explain why this is the proper analog in a moment, but you can think of it as maximal ideals represent points, and when we do the switch from algebra to geometry, the order switches. So this represents a point contained in this algebraic set that is generated by I. Now, we could have defined this for an arbitrary subset instead of for an ideal, but we would have gotten even more simply than before that V of some arbitrary subset is the same thing as V of the ideal generated by that subset, and that's just because if a subset is contained here, the ideal generated by it is also contained here. So we are going to take these sets and we are going to take them as closed sets, and that is going to give us a topology, which we'll call again the Zariski topology on MaxSpec, and we claim that this is exactly the same topology when we plug in the coordinate ring. And I claim that this topology will recover, at least up to homeomorphism, the algebraic set V when we plug in V's coordinate ring. Let's explore this coordinate ring perspective a little bit further. So in the classical case, a polynomial f, as we said, defines a function on Kn by evaluation. Now we can think of these evaluation morphisms as the image of f under a quotient homomorphism. So if we take the quotient map from x1 up to xn, the maximal ideal, which I'm going to denote MA, that's defined by A, this is canonically isomorphic to our base field, and if we take f here and we project it, then we get f of A, exactly. So we can think of evaluation at a point algebraically as identifying that point with its maximal ideal and looking at the image under the quotient map corresponding to that maximal ideal. Now in this case we're lucky that quotienting by every maximal ideal just gives us back the base field. But in general, we're going to have to be a little more lenient and ask for a function not into a single field, but a function that takes values in a variety of fields. So a bunch of varying fields. So for an element R of an arbitrary ring, we think of R as a function from MaxSpec into this disjoint union of fields indexed by maximal ideals. And of course, then we can define the evaluation. R of M is just the image of R under the quotient map in this residue field of the maximal ideal. And this mirrors our definition for polynomials. Having defined this function, we can still talk about zeros of a function, because in every residue field we have a zero element, obviously. So we can talk about the closed set defined by an ideal I, and we can equivalently define that as all the maximal ideals such that R of M is 0 for all R in I. In other words, the collection of all points that vanish on all of these functions in this ideal in the coordinate ring. So now, obviously, if we plug in a coordinate ring, then MaxSpec is just going to be the set of maximal ideals, which is bijective to the set of points, and the closed sets are going to be exactly the same closed sets. In other words, V of I is going to be, I is a set of functions in the coordinate ring, so it's going to be all of the maximal ideals whose corresponding points are vanishing points for all of the elements in the ideal. So this is obviously the same thing as just the algebraic set again, at least again topologically, up to homeomorphism. We still haven't captured any extra geometric structure. So now we have this thing that maps rings to geometric objects in a way that we can kind of retrieve the classical case. The next thing is to try and turn this into a functor. In other words, we want to understand how we can define maps between MaxSpec. At least given maps between rings, what are the correct maps between MaxSpec? So to do that, we're going to go back and try and see what the correct maps are in the classical case. So the obvious thing to look at is maps which are themselves polynomials, because all of the structure we're dealing with comes from polynomials. So given varieties V in Kn and W in Km, so these are algebraic sets, then a morphism is a function f from V to W such that it is given by polynomials. So there are m polynomials inside the polynomial ring in n variables, such that f is just these polynomials restricted to V. So for every element x in V, f of x is just given by these m polynomial functions. And this is of course an element of W, which is a subset of Km. Now, unfortunately, this notion of is given by polynomials is not very easy to generalize to arbitrary rings. But we can actually give another description of these maps by trying to extend the analogy between algebra and geometry. Another good guess for what the correct notion of map should be would be to try and extend the analogy from algebra to geometry again. So we have these algebraic objects which are coordinate rings, and it's obvious what the notion of a map between coordinate rings should be. Now you might think that the correct notion would be ring homomorphisms, but actually the correct notion should be K-algebra homomorphisms, because it is important for us to remember that we are over K, our sets are defined over K as polynomial rings, where the constants are exactly the elements of K. So given these K-algebra homomorphisms, we can try and convert that into a map of algebraic sets. So given such a homomorphism, it's actually a fact that the inverse image of a maximal ideal M is maximal, so when M is maximal. Now this is not generally true. Generally, the most we can say is that the inverse image of a maximal ideal is prime, and that's actually going to be an important note in the ensuing discussion. But in this case, the inverse image is actually maximal. So now we get a map from MaxSpec of W to MaxSpec of V given by this inverse image. Surprise, the arrow is reversed. And this actually gives us an induced map, V # from W to V, where this map maps P to Q if the inverse image of the maximal ideal of P is the maximal ideal of Q. So in other words, it is the corresponding map of points to this map of maximal ideals. And now we can ask ourselves, what structure do these maps have? And it turns out that these maps are exactly the morphisms. They're exactly maps given by polynomials, and moreover, given a map given by polynomials, we can canonically construct a K-algebra homomorphism just using precomposition. So that gives us a bijective correspondence between these polynomial morphisms and K-algebra homomorphisms with the coordinate ring. Now, these algebras have some properties, namely they are always finitely generated and they are always reduced. So putting this all together, we get a functor from affine algebraic sets over K to finitely generated reduced K-algebras, and we put an opposite category here because this is a contravariant functor, which means that when it takes a map, it flips the direction of the arrows, as we saw. And this functor is of course defined by taking an algebraic set to its coordinate ring and a morphism to the induced morphism given by precomposition that we described before. And this functor, for those of you who know what this means, is actually an equivalence of categories. So this gives us a duality between affine algebraic sets and finitely generated reduced K-algebras. Now we want to try and do the same thing, but for general rings. So in other words, if we have a morphism, a homomorphism of rings S to R, now we don't have any base field to remember, so we're just looking at ring homomorphisms, then we want to define an inverse image map on MaxSpec. So MaxSpec of R to MaxSpec of S. Again, we now given exactly as before by the inverse image. Now the problem is, as we said before, that the inverse image of a general ring map of a maximal ideal is not going to be maximal, but prime. That means that maybe we need to broaden our definition a bit and introduce some redundant information by keeping track of the prime ideals, which would correspond to irreducible closed subsets both in MaxSpec and in the classical case. And we think of these as generic points of these irreducible closed subsets, where a generic point is a point whose closure is the entire space. And indeed, there's going to be a lot of weird topological stuff when we actually define the prime spectrum. But for all that and more, join us next time when we're going to be talking about the prime spectrum and maybe sheaves, hopefully soon. Until then, keep doing cool math, and I'll see you next time.